Today we're going to be working on Le Chatelier's principle and some ideas about what equilibrium means and how it works in the solution phase. So what we're going to be actually working with in this first part of the experiment is a little bit of potassium chromate. We're going to be changing it from the chromate to the dichromate. We're going to get started by just taking a few milliliters of the potassium chromate and adding it to the graduated cylinder we have here. It's got a nice yellow color to it, which is worth observing to start with. We're just going to take 1 to 2 milliliters, and we're going to see, we don't need, by the way, too much today because we're just looking at the color change. We don't need to be too exact. We're going to take that, we're going to add it to a test tube here, and let's try to take a good look at that color. So if you look at it closely, it's a totally clear solution. There's no precipitate. You want to make sure that you always are working with a clear solution to start with when you're doing any kind of equilibrium work. Why is that? Mostly because none of these compounds will really react very well if they're in the solid phase. You want to make sure that you're always working in the solution phase. You have to be fully aqueous ions for what we're doing today. We're going to be actually starting with the chromate moving to the dichromate by adding acid. By adding acid, we're going to actually be turning this ion to dichromate by protonating the oxygens and forming water as a byproduct. So let's just add a couple drops. And already you can see as you agitate it, it becomes an orange color. So immediately, right away, the equilibrium is pushed, and you can actually observe this by this change in color. Right? Sometimes you'll see it won't be quite as visible. You might become, maybe it'll form a colorless species, it'll become a little bit lighter, not as obvious. But in this case, the dichromate is orange versus the chromate being yellow. Let's add a little bit more and see if we get anything else. So it's any darker. All these observations are worth noting, and as far as I can tell, we only got a little bit more orange. That's about it. And so we're gonna go the opposite way here. We just added some acid. We pushed it from chromate to dichromate, and now we're going to add a little bit of base. Adding some sodium hydroxide, and we're going to see how that goes. Already, you can see the bottom of this has become yellow. As you mix it around, might need a little bit more. It's more concentrated, but it's not working quite as fast. Let's just totally go after it here. And we've restored it to the original color. We're back to yellow again. Also, this container's getting pretty warm here. So here you can see the layering pretty well. Where there's more acid at the top, the color's already changed. It's almost like there's even a phase boundary there. When we mix it up, sulfuric acid Not quite enough. Let's get a little bit more. Oh yeah. Looks like we're getting closer to that dichromate being the main species in equilibrium. For the sake of this video though, we're going to call it good. And this is what you'll observe in the case of this equilibrium. Remember, you don't have a complete removal of either of these species. There's always going to be some concentration of chromate, some concentration of dichromate. That's very useful to remember because you're not eliminating any particular species here. There's always going to be a little bit of hydroxide no matter how concentrated the hydronium in any solution is. It's a matter of relative concentration. So now we're going to look at a little bit of acid-base equilibrium, and specifically the common ion effect. We're going to be working with a little bit of acetic acid and sodium acetate, and we're going to look at the way that acetic acid, which is a weak acid, is going to also be in equilibrium with acetate, its conjugate base. If we add the conjugate base, we're going to be adding a base to the solution, so you're going to be increasing the pH. And if you add more of the acetic acid, you're going to add the protonated version of that species, and that's going to push it back to the acidic side. We're going to be able to observe this using a little bit of methyl orange. And methyl orange is right here, that we were using before, and it's just favorable because it works more in the acidic side as the color changes. You're going to actually observe that color change at a much lower pH than for phenolphthaleate, for example. So first we're going to measure out a little bit of acetic acid, about 1 to 2 milliliters per test tube. So you don't have to be 100% exact here. Again, we're just looking at the color change, so do what we can. If you're doing some kind of analytical work, that's a different story. So let's take a look here. See, we already have about 3, so I'm going to add get up to 4 milliliters and split it between these 2 test tubes. Passed. And I'm going to just add this. I just added all of it. No big deal. So I just added 4 milliliters of 0.1 molar acetic acid to this test tube, and for the sake of this demonstration, I'll just add the same amount to the other test tube, so as not to waste it. So we only need a single drop of methyl orange. Again, any kind of indicator you're working with, you're always going to only need a tiny bit for a really good indicator. So we've got 2 acidic solutions here, and if you remember from the last experiment with the methyl orange, this is the color that appears usually when it's in the more acidic side. Both of these 2 test tubes are still exactly the same. 1 drop of methyl orange per with 4 milliliters of the acetic acid, 0.1 molar. So now we're going to add 1 molar sodium acetate, a few drops at a time. Eventually, we're going to see a color change, and I'll try to count out these drops for you so that you can actually make note of that. So we have 4 milliliters total. Remember, it's 20 milliliters, 20 drops per 1 milliliter. It's going to change the portion there. All right, so we'll take this first test tube. We're going to add slowly until we get a color change. So 1, 2, 3, 4, 5. Mix that up and see if we actually get a color change. Didn't take much at all, so about 1/4 of a milliliter, maybe even less. Next time we'll go a little slower. But for now, we already saw a color change. Could have probably even done with less than that. Kind of overestimated it there. No big deal. So that's sodium acetate. And that was able to bring the pH up a little bit to where we observe this color change. But 2 milliliters would have been even quicker. All right, next we're going to look at ammonium hydroxide. And so ammonium hydroxide is going to be right here. Another kind of base, going to be adding different cation here, the ammonium ion. All right, so this time I'm going to go a little slower. So we're going to add a little bit of ammonium hydroxide, stir it, still no real change. Other drop, second drop, so now the third drop. No color change yet. Fourth drop. Fifth drop. We're getting there. Sixth drop. Seventh drop. Eighth drop. Ninth drop. 10th drop. 11th drop. And that appears to be sufficient. So even though they're the same concentration, the base, we ended up taking a little bit more, maybe another 2 drops. In order to actually change the pH appreciably in this situation. Yep. This one still isn't even quite as acidic as this one. That has mostly to do with the common ion effect, which has to do with equilibrium related to similar anions working in equilibrium. So now we're going to look at the equilibrium between iron and thiocyanate, forming the iron thiocyanate cation. We're going to have 1, or test tube 1 rather, as our control, test tube 2 as our addition of extra potassium thiocyanate. We're going to add some extra iron nitrate to test tube 3. And test tube 4, we're going to add a lot of base and just see how that affects the equilibrium to see where the reaction goes from there. So let's start by taking our iron nitrate, which is going to be our iron 3+ source, and add 3 milliliters of that to this Erlenmeyer flask. Just measure that into this graduated cylinder. Again, we're just looking for color. We want to be close, but not really stress too much. Looks like we're a little over 3 there. That's fine. Let's go here. And we're going to add potassium thiocyanate. They're going to mix together anyways. Just make sure you do not touch the tip of this pipette to this graduated cylinder, and you shouldn't have to worry about any cross-contamination. That's the key. Do not touch the tube. Oh wow, look, there it goes. You can see already reaction with the iron. That's pretty fun. Quite evil looking, almost like bromine. And that's all we need. And you just take these 3 milliliters and add them to the aerosol flask. I'm going to wash that down with a little bit of DI water right here, so we don't lose any. Keep all that color if we can. If you look closely, you can see that's like the concentrated color. It's almost like a Cabernet Sauvignon, a very deep sort of wineish red color that is virtually opaque because it's just so dark. But we're going to dilute that just so we can see a little bit better with about 60 milliliters of DI water.
I'll give us a little bit more to see here. That was 15 milliliters, another 10. Yeah, 13. Oh, just throw it waste here. Yeah, at least a little close. There we go, that's closer.
And still, it's pretty dark. You have overall stark reddish, almost purple color. Closer to a Merlot, maybe a Shiraz, I don't know, hard to say. So here we have our solution that we're going to distribute amongst these 4 test tubes. So let's make sure you can see those. And I'm going to add, just by a little finesse, about 5 milliliters to each. Yeah, that was a little full, that's fine. They're all pretty close in volume. We're just going to start adding different reagents to them to observe roughly what the effect is on this equilibrium. Add that 1 milliliter. So let's see what we got here. To compare it to the control, it appears to have gotten a little darker. It's hard to say. It appears to be a little darker than when it started. We're going to add 1 mil to the tube 3. And let's see, 1 milliliter. It's about 1 milliliter. And so just make sure that we add it all in there. Try to place that. Hard to say, but it doesn't look like it changed too much. Maybe it's a little bit lighter. Let's compare it to the original. And then finally, we're going to add a little bit of 6 molar hydrochloric acid. And by that I mean, sodium hydroxide. So we're adding 6 molar sodium hydroxide. We're going to add 5 to 6 drops of that. Checking my notes there. Actually, it looks like we already have 5 to 6 drops that I left over from before. And I'm just going to add that here. It's hardly a drop at all, so let's see. 1, 2, oh, alright. So we add only a couple drops really, and already have a substantial change in color. About 5 drops there, and then we add last drop here. And it looks like we even have a precipitate forming there, which is going to be, what do you think? So this is actually what we would call iron hydroxide, right? And when something leaves solution, what's happening? Is it still in equilibrium? No. So once you have the solid form, it has left chemical equilibrium and has fallen out. So it's not going to really participate in the same kind of equilibrium that's happening in the aqueous phase. So it'll rapidly cause other stuff to fall out of solution, kind of moving in the same direction as it's disappearing on, let's say, the reactant or the product side. It's going to pull more reactants across the reaction, pushing equilibrium to the right. The potassium thiocyanate got a little darker. Adding more iron nitrate didn't do much, and adding just a little bit of sodium hydroxide made a world of difference and created a little bit of precipitate there, lightened the color drastically. Metal ions will have different interactions with the solutions that they're dissolved in. You could have cations, anions, and other kinds of molecules that will enter and leave the coordination sphere of any particular cation that you're working with. So depending on what kind of ion you're looking at, you could have a stronger interaction with certain cations and anions or regular neutral molecules, or a weak interaction. If you have a different, stronger interaction, you're going to have those cations, anions, or molecules entering the coordination sphere of the cation that you're interested in, the metal cation, and they're going to sit on the edge of that coordination sphere and potentially change the color of that individual species. It's going to become a new species which has a new color. We're going to use temperature, also a little bit of thermal agitation, to actually see how cobalt chloride can do that. So let's find that cobalt chloride. Put the sodium hydroxide back here. Potassium thiocyanate. Here we have some cobalt chloride. And it's 0.15 molar, it's pretty dilute. We only need about 4 milliliters of it. Cobalt chloride, which in this case is going to be the methanol coordinated version. It's going to have a light purple color. And it's going to have a little bit of water coordinated, only 2 portions. Now remember, that water isn't bound to it covalently. It's just loosely interacting because the polarity of that water is interested in interacting with the coordination sphere, or just the electromagnetic space around the cobalt, and affecting its color. Alright, so what we started with is we took a little bit of cobalt 2 chloride and methanol, which is going to be the cobalt coordinated with 2 water molecules, and we added a little bit of water to it. So here is that original solution. This solution right here is pretty purple at this point. It's kind of like a grape juice. And we added a little bit of water, which we're going to split up between 2 test tubes. So you can see the difference in color. It's not a huge difference in color, but you really don't want to go too far, otherwise you're going to have a little bit too much water and the reactions won't actually go forward as we hope them to. So in this case, we have the hexa-coordinated or 6H2O complex of the cobalt, and this is the di-coordinated version, or the 2 H2Os per cobalt version of the cobalt chloride solution. here we are with the two test tubes, pink color, and we have hydrochloric acid, concentrated 12 molar hydrochloric acid. Into the first test tube, we're going to add a few drops till it changes color. Now we're going to also be adding a common ion in this case, so the chloride ion is the common ion for cobalt chloride, and that'll also be affecting equilibrium, pushing the reaction one direction or another. I'll let you decide. Can't give you all the answers. We're going to add hydrochloric acid until we get a color change. Try to add it directly to the solution so you get effective mixing. If you lose any on the sides of the test tube, you might have already added too much. This is as good a color change as we're going to hope for in this case. So, sort of like a bluish color at this point. Similar to the cobalt blue that we're looking for. But also kind of purple, I would say. Alright, so that test tube we're going to take and we're going to actually put it in this bath of hot water. Been heating for the better part about half an hour. Now take note of the starting color, which is a blue color at this point. Quite blue actually. Beautiful blue color, to be honest. So now we're going to add the other test tube to this hot bath as well. See if we actually get another color change. So now what we're going to do is we're going to take these two solutions and place them into an ice bath. So make sure you take note, the blue one is going to be the hydrochloric acid solution, and the pink one or purple one is going to be the other solution, which is going to have no addition of hydrochloric acid, just heat. We're going to place these two solutions inside this flask and observe any color change we can. Make sure that you always record any changes in color whenever you see them. Already seeing a little bit of a change. The solution right here with the hydrochloric acid is becoming more and more purple. And the solution is becoming a little bit more red. In the case of an endothermic reaction, if you add heat as a reactant or a starting material, you're going to be ending up pushing the reaction to the right. For an exothermic reaction, you're actually going to be pushing the reaction to the left. Now, depending on whether or not you're removing heat with an ice bath or adding heat with a hot water bath, you can kind of predict roughly what sort of reaction you're working with, whether it's endothermic or exothermic, just by the use of temperature alone. So these are about as cold as they're going to get. Make sure that you record the observations for any of the temperature changes and the color changes that you notice, and make sure that you follow them in the order that they were added, just to make sure that you are keeping track of the different expected changes as they happen. So we have this solution back to a pink, or even more of a purple, and this solution went from a full-on blue color back to a purple. I'm going to put it back into the heat for a second and see if it changes back, and then we'll call it good. And that was rapid. Wow, that happened really fast. So right away, we saw it change right back to blue. The reaction on the left didn't change very much, but also there's probably not a lot of methanol left in there because it probably got heated out. By adding ions to a solution, you're going to end up adding higher concentrations of one ion, which might push another ion out of solution. Or sometimes, in the case, you'll push a solid completely out of the solution. In this case, we're going to be working with some saturated potassium chloride, and we're going to try to get that to precipitate by adding the common ion, chloride, and make it fall out as potassium chloride crystals by reaching its supersaturation or oversaturation point. We're then going to try to see if we can redissolve that and get it back in solution. So at some temperatures, you're going to have higher solubility than others. Let's see how this goes. Hopefully you can see a really clear precipitation happen. For potassium chloride, you would expect to have an extremely high solubility. Potassium is an alkali metal. It's going to be a great cation, in solution as well. And chloride is usually relatively soluble, depending on what kind of metals it's in solution with. So here we're going to take, in this case, 4 milliliters of saturated solution. Doesn't matter exactly how much, so I'm going to just eyeball it on this in this case. You don't want too much because it won't heat as effectively. About 3 of these should be plenty. Yeah, that's perfect. So you have about 4 milliliters in here. And we're gonna actually, before I heat it up, you can see that it's totally clear and it's a colorless solution. So what we're going to do is we're going to add some of this 12 molar hydrochloric acid. And the 12 molar hydrochloric acid is going to essentially introduce lots of chloride ions to the solution and knock it out of solution as potassium chloride. And you can see already, right away, despite how soluble this should be, the 12 molar hydrochloric acid is knocking the KCl right out. So to get this back into solution, which will be pretty hard to do at this point because it's quite concentrated, we're going to see what we can do by dissolving this KCl with this hot water in this bath. So take a close look at how much KCl is in there right now, and then see how much of that disappears as you apply heat. Once you redissolve that KCl into solution, the cations and anions, potassium and chloride respectively, are going to be available for different kinds of equilibrium and equilibrium effects. For now, when they're locked up in the KCl at the bottom of this test tube, they're not very useful for any kind of solution phase interactions. So it might be hard to tell, but it looks like we've actually dissolved some of this KCl. I'm going to turn up the heat a little bit. As you can see, it appears that we've eliminated a lot of that KCl. Let's see if we can't get the rest of it, but it's almost all gone. And with a little stirring, all of a sudden, we have virtually no KCl left, and this saturated solution, which if we cool down will actually precipitate again, is clear once again. So let's observe that. Since we have an ice bath available, let's take a look and see if we can't get it to fall out of solution again. if you carefully crystallize these very, very slowly, you could potentially actually grow very large crystals that would be highly ordered. And they could potentially even be, if you can see them, millions, billions, or even more atoms across in almost perfect order. But to get that kind of order, you need extremely stable crystallization conditions, and the temperature change has to be extremely slow. These crystals will probably be good, but they won't be as ordered as they could be. Already you can see the crystals begin to bloom as I agitate the solution. They were just waiting for their chance to escape from the solution into the solid phase. Like a snow globe.